Classical machine learning pipelines are exceptionally efficient tools. When presented with small, pristine tabular datasets, standard algorithms can extract predictive patterns with high reliability. But real physical industrial environments do not generate clean spreadsheets. They produce chaotic, unpredictable, and high-speed continuous motion. When confronted with dense, noisy inputs, like multi-channel vibration streams or high-resolution imagery, standard processes fail. Analysts run into the feature engineering bottleneck. Human programmers simply cannot write manual code complex enough to extract actionable parameters from these high-dimensional data streams. Deep learning provides the necessary structural shift to process this volume of noise. Its primary advantage is the ability to perform end-to-end hierarchical representation learning. Rather than relying on human engineers to handcraft specific rules, deep multi-layer networks process the raw input directly. They automatically discover successive mathematical representations, compounding them into increasingly abstract features layer by layer. Deep learning architectures provide the necessary mathematical framework to convert raw sensory modalities into accurate, reliable predictions on the factory floor. The foundation of this processing power is the artificial neural network. It is a structure composed of interconnected processing units, or neurons, arranged in sequential layers. Data moves through the structure via a forward pass. The network transforms raw inputs by calculating linear combinations and then applying nonlinear activation functions, which allow the system to map complex relationships. This graph illustrates gradient-based optimization. Backpropagation calculates the loss function, and gradient descent adjusts internal weights to seek the lowest error. But models overfit, memorizing data. To generalize, we use regularization. Increasing weight decay and dropout ignores certain connections, learning robust features, which stabilizes the loss curve. Recent models improve this process through gradient-enhanced learning. Instead of solely training on function values, these models ingest actual derivative information during training. Explicitly calculating these derivatives drastically reduces approximation error, yielding tighter mathematical representations and giving the system a way to quantify its own uncertainty. Raw processing units hold no inherent value. Strict optimization and mathematical regularization are the actual engines that allow industrial networks to generalize across new data. Let's apply this mathematical structure to visual inspection. Factory floors rely heavily on grid-structured sensor arrays and optical cameras to monitor production quality. Standard neural networks fail here. They process inputs as flat, one-dimensional lists, which destroys the inherent spatial structure of an image and scales terribly when processing millions of pixels. Convolutional neural networks, or CNNs, are designed explicitly to solve this problem, making them the dominant architecture for spatial data analysis. This diagram shows a CNN in operation. The network slides localized filters, known as kernels, across the grid, extracting local features into a condensed feature map. This mechanical sliding creates translation equivariance. The kernel calculates the exact same activation output for a specific shape, regardless of its position. This mathematical constraint allows the network to identify microscopic fractures on a metal surface or complex cultural patterns like Timorese weaving motifs, even as the textile moves or shifts across the camera's field of view. By cascading multiple CNN layers into designs like UNet variants, models can perform precise pixel-by-pixel segmentation of defects, even when supplied with very limited labeled training data. To solve problems bound by physical space, the network's architecture must be mathematically constrained to mirror the localized, grid-like geometry of that space. Moving from spatial imagery to temporal data changes the structural requirements entirely. Industrial facilities generate continuous production logs and massive vibration time series streams. Standard feed-forward networks have zero internal memory. If you feed them a sequential stream of logs, they process each input in total isolation, failing completely to map sequential dependencies. Recurrent neural networks, or RNNs, solve this by looping information. They retain an internal state, passing data from previous time steps forward to influence the current calculation. However, standard RNNs collapse when faced with long industrial sequences. Over thousands of time steps, the mathematical gradients diminish to zero, a vanishing gradient that permanently erases early historical signals. This schematic visualizes the necessary architectural fix, a gated recurrent unit, or GRU. Advanced recurrent architectures utilize mathematical update and reset gates. These compute dynamic thresholds, actively deciding which historical data to retain in memory and which irrelevant noise to discard, generating a refined output vector. Tracking industrial time requires these gated architectures. Without them, it is impossible to isolate critical failure signals from an infinite stream of background temporal noise. Physical phenomena do not neatly divide themselves into pure space or pure time. Real-world dynamics require tracking both simultaneously. Consider an active construction site. Heavy machinery operates with complex spatial geometries, moving rapidly across long operational timelines. Analyzing this requires a spatio-temporal hybrid network. This topology places a convolutional neural network at the front end, which feeds its output directly into recurrent or attention-based layers. The CNN mathematically strips out the localized spatial patterns, the position and shape of the equipment, and passes those compressed feature maps to the recurrent layers, which map the long-range temporal dependencies of their movement. These hybrid models are strictly required for high-complexity tasks like construction duration estimation, where both geometry and historical duration dictate the outcome. Real physical reality is dense and overlapping. The highest-value industrial algorithms fuse structural topologies to match that exact complexity. There is a severe constraint in applying these architectures. Unlike theoretical research domains, manufacturing environments rarely possess millions of perfectly labeled data points. Attempting to train a deep, multi-layer network from scratch on a small domain dataset guarantees severe extrapolation failures. The model will collapse when presented with any variance on the factory floor. We mitigate data scarcity by utilizing transfer learning. This diagram illustrates transfer learning. We take a massive network trained on a data-rich domain, like medical tumor segmentation, and transplant those pre-trained weights into an empty manufacturing network. We then feed our small batch of industrial data into it. The network only fine-tunes its outermost layers to detect specific factory defects. Transfer learning is combined with continuous learning and aggressive 3D data augmentation. By mathematically rotating, cropping, and masking the limited training images, we artificially multiply the dataset, forcing the network to recognize the target from multiple distorted angles. As factory environments physically change, the data undergoes distribution shifts. Applying incremental retraining to the model captures this drift, allowing the network to adapt without forgetting past patterns. This chart tracks accuracy on a difficult multi-level aerosol image task. Using static data, the performance stalls near 60. This distributed IoT hardware produces data that is highly variable across different locations. To train unified models on this fractured data, systems employ federated learning. This diagram maps the federated mechanism. Individual edge sensors train localized models using their own distinct inputs. They transmit only the algorithmic updates back to a central server. The raw data never leaves the local machine. As researchers develop quantum-inspired layers and quantum tunneling activation concepts, these decentralized central hubs can further enrich the feature maps, pushing highly optimized model updates back to edge hardware with strict power constraints. This is the baseline requirement for autonomy. Thousands of localized networks cooperating in real time, completely synchronized through continuous architectural updates. Modern industrial monitoring relies on deploying specific network typologies that allow a physical facility to accurately and continuously decode its own performance.